In case I'm not able to make it into the labs this week, this is a short introduction video to the Week 5 Analogue labs about the bandwidth of OpAmp amplifiers. First, a quick reminder about opamps. When opamps are not saturating, then you can assume that the output is doing whatever it has to do in order to make the difference between the two inputs as small as possible. We've seen this configuration before. If it's not familiar, then go and have a look at the short introduction to opamps on the module website. But this is the formula for the gain, the output divided by the input, of a non-inverting opamp configuration, where the input is put into the non-inverting input here, and the output feeds through a potential divider back to the inverting input. For an inverting amplifier, the output is -1 times the feedback resistor, R2, divided by the input resistor, R1. Again, the derivation is fairly straightforward. We've seen it before. It's in the lecture notes and the short introductions. Now, before we get on to looking at the bandwidth of op-amp circuits, there's one part of the VAM that we need to design and finish building, and that is the power supply section. The last part of that is to generate a mid-rail voltage. That's a voltage halfway in between the 0 volts, ground, and the 3.3 volt power that we'll use to power most of the op-amps in the audio part of the VAM. What we're trying to do then is to produce a low impedance voltage source, such as the output of an op-amp, which is held at halfway between 0 and probably around 3.3 volts, the voltage of your derived power supply. That's around about 1.65 volts or so. And in order to do that, there's an op-amp on the board which is fed by the very stable voltage generator that should already be fitted on the VAM. That gives an output of about 1.22 volts. So we need an OpAmp amplifier which will amplify that 1.22 volts to about 1.65 volts. And that's an ideal application for a non-inverting amplifier like this. Your first task is to find two suitable resistors to put in the feedback loop for the non-inverting amplifier to give you the gain that you required. 1.65 volts out, 1.22 volts in. And then before you build it, it's a good idea to check that your values are sensible, and there's a simulation preset that can help with that. Under the VAM design preset group, there is a mid-rail, VAM mid-rail, that one, and that will produce this diagram, which will give you the output from a 1.22 volt voltage reference, which you should already have working, through a op-amp with gain set by this resistor and this resistor. And you can see that just using two 1K resistors is not a very good idea. You get 2.44 volts. It's also suggested that the resistance values that you use are somewhere between 10K and 100K in the lab script. And that's due to the fact that using lower value resistors increases the current, and that just wastes power, really. Using any higher values than 100K makes the circuit a bit noisy. We'll talk a lot more about noise in the summer term. So you'll need to change the values of these two resistors so that they're both within the range of 10K to 100K, and you get an output which is as close as you can to 1.65 volts. When you've got that and the simulator agrees, you can build those onto your VAM board. The next thing we'll do is start looking at the bandwidth of actually real OpAmp amplifiers. And we'll investigate these by plotting the Bode plot of their frequency response. Now, that means plotting the amplitude gain in dB on the y-axis against the log of the frequency on the x-axis. So, for example, Log of 100 is 2, log of 1,000 is 3, log of 10,000 is 4, log of 100,000 is 5, and so on. In terms of the logs, I've got 2, 3, 4, 5, and 6 on the bottom on the x-axis, but I've labelled them as 100, 1k, 10k, 100k, because it's easier to read. These are the actual frequencies. If I take a lot of readings at the gain at these different frequencies, I should have some points which lie on this shape of curve. It starts horizontal. At higher frequencies, it's going down at 20 dBs per decade. So between here, 100k, and here, 1 megahertz, it should have dropped down by 20 dB. And in between, there's a curvy bit. If you extrapolate the low frequency straight line and the high frequency straight line, they meet at this point here, which is known as the break or corner frequency. And at the break or corner frequency, the gain should be 3 dB down on the low frequency value. That is the theory. We're about to try and see if it actually works in practice. The first thing we'll have to do is build a OpAmp amplifier. A non-inverting OpAmp amplifier is the first one in the lab. This will require getting a split rail power supply, so plus 12 and minus 12 volts from the lab power supply unit. If you're not sure how to do this, there's a document about it on the lab webpage. Have a look at that one first. There are a few traps for the unwary. We can also build the circuit on one of the breadboards, and to make sure that your breadboard layout is accurate, the simulator can help with that. There's a preset under Spring Labs, Lab 8 Sample Layout, this one. Actually, no, we'll just start with Lab 8 Non-Inverting, because this will produce a very simple non-inverting amplifier with an input A, an output X, a gain of 101 in this case, and a split power supply of plus and minus 12 volts, and a layout part down here. And your task is to make the layout here such that when you press check design, you don't get any errors or warnings at all. Have a go yourself. It's good practice learning about how breadboards work. If you put the cursor on any hole on the breadboard, then all of the other holes attached to that hole light up, as you can see. And we've got to do something like the power supply as well. I could put the minus 12 volt power supply down here and just hook across to there. That would give me my minus 12 on pin 4 of my op-amp. My plus 12 could go across to here and it down into power pin 7 to power the op-amp, and so on. Have a go at arranging things. As I say, it's good experience. If you get completely stuck, then there is a sample solution to it in the simulator here, which you could use and just copy. The sample layout also includes two so-called decoupling capacitors, 100 nanofarad decoupling capacitors, which I've put in my layout here. They go between plus 12 and ground, and between minus 12 and ground, and their job is to just make the power supplies quieter so that they remain a constant value all the time. And if you've got your wiring up all right, then you should be able to press check design and get a nice reassuring no issues found here. That means that your design is going to work. You are free to continue and build it. The A input here should come from the function generator. The X output there should go straight to the input channel of the oscilloscope so that you can measure the output signal. And the other inputs come straight from the lab power supply unit. Having measured the 3 dB bandwidth of that amplifier with gain of 101, you should be able to deduce the gain bandwidth product of the op-amp that you're using. This should remain constant for any circuit built using that op-amp. And we can test that later by building a completely different circuit, a summing amplifier, using the same op-amp and predicting what its 3 dB bandwidth is going to be before we try and measure it. If all works, and it should, this should give us a very accurate prediction of the 3 dB bandwidth of the summing amplifier. There are some presets built into the simulator, but a reminder, if you are going to build your own circuits from scratch, remember to use the bandwidth limited op-amp model, which has these twiddly lines in the middle of it and a gain bandwidth product, in this case 15 MHz, written next to it. The ideal op-amp model in the simulator has an infinite gain bandwidth product, which isn't going to be very helpful when trying to predict a 3 dB bandwidth. A quick reminder about the single op-amp package that we'll be using in this lab. The pins are numbered anti-clockwise. Remember, everything goes anti-clockwise except clocks. They start at the corner here with the dot, and they number 1, 2, 3, 4, 5, 6, 7, 8 round in that order. And this is the industry standard pinout for a single op-amp in an 8-pin package. Remember, op-amps are active components as well. They don't work without power. They will require a positive power supply on pin 7 and a negative power supply on pin 8. Also make sure that all of your grounds from the power supply, from the feedback resistor circuit, from the function generator and from the oscilloscope are all connected together. Also, reminder about measuring small amplitude signals on the scope, and at high frequencies you are going to be trying to measure some very small amplitude sine waves. Switch on averaging, but make sure that the oscilloscope is stably triggered. It has a nice big noise-free waveform to trigger from. And the easiest way to do that is to take two outputs from the function generator. Either use both channels and set them to the same frequency, or use a BNC T-piece which splits off one output so you can take two BNC cables away from it. Take one to the input of your op-amp circuit and take the other one to channel 2 of the scope. Once you've got a nice trigger, you can turn on averaging. That will help to reduce the noise. I'd also suggest that you plot the points as you go along. This can save a lot of time if you find you're taking an awful lot of frequency readings at very low frequencies, all of which lie on a straight line, then really you're wasting your time. I'd suggest taking readings at the decades of frequency. So maybe 10 Hz, 100 Hz, a kilohertz, 10 kilohertz, 100 kilohertz, a megahertz, and then have a look and see where the graph is doing something interesting, where the points do not lie on a straight line, and take a few more readings around those points. You're trying to accurately find out the frequency at which the gain has dropped by 3 dB, the so-called 3 dB bandwidth. Reminder about breadboards as well. The breadboards in the DASIM simulator are only half of a breadboard in the lab. The breadboards in the lab are twice as long, but remember that the two rows here in the power rail are not connected to the two rows here in the power rail. There's a blue line here and a red line here which do not join up with the blue lines here and the red lines here, and they don't for a very good reason. The pins are not connected. Best thing to do is to just use the top half of one of the boards. Make sure if everything is in the top half of a breadboard and you should be fine. You could use the breadboard utility thingies if you like. Reminder, if you do, all the ground connections should be connected together somewhere. And if you're taking the output from one of these coax cables straight to the scope, remember to set the scope input channel to ×1. Couple of frequently asked questions I will leave you to read. There are some answers to these and others on the wiki page for the lab. That's about all for this time, except that the JavaScript simulator is not new this year. The slide is just old. That's the end of this one. I'll do another short chat about the second half of this lab as well.